Good afternoon. Thanks for coming to this session. Who's here at reInvent for the first time? Awesome, welcome. Should be an exciting week. Lots of sessions, lots of parties, lots of fun. So I am Peter Vosshall. I am a distinguished engineer at AWS. And today I'm going to talk about how AWS minimizes the blast radius of failures. So I spent my career focused on building highly available, large-scale distributed systems. And one of the things I've learned, and something you learn quickly in this field, is that there are some fundamental properties of the universe that you basically have to contend with. The first is the speed of light. So 186 miles per millisecond is pretty darn fast. But as the folks at JPL this morning trying to land their Mars rover learned, it really gets in the way when you travel any long distance in communications. By the way, they did land the rover successfully, so congratulations to our friends at JPL, a happy Amazon customer, AWS customer. The next thing is sort of this pesky property of the universe known as the CAP theorem. So this is an observation that you can't simultaneously have consistency and availability in a distributed system that is built to be partition tolerant. So this was first postulated by Eric Brewer in '98 and then proven by Seth Gilbert and Nancy Lynch at MIT. Perhaps most annoying, though, is this observation by some guy named Murphy, which is basically stuff breaks. Inevitably, things will fail in a variety of interesting ways. I don't know if this has been proven, but in my experience, it seems to have been borne out to be the truth. Now, security, availability, durability, these are all super important to AWS. In fact, they're our top priority. And yet, we have to contend with Murphy's Law. So today I'm going to talk about the techniques that Amazon uses, that AWS uses, to contain the blast radius or the degree of impact when Murphy's Law does in fact strike. And I hope you walk away from this talk getting a better understanding of how AWS builds resilience into our systems, and also some techniques that you can use to reduce the blast radius in your own systems. So this term blast radius it's a really useful one because failure isn't binary. It's failing or it's not. There is a degree of impact. And it's a really useful term. It's part of our common language at AWS. And basically, it's a way to describe the degree of impact. So at AWS, if we have a failure, one way to talk about blast radius is, well, how many customers did it impact? Or how many workloads? Or what functionality? Maybe it was just a portion of the functionality that was impacted. And then finally, in what locations? Was it a rack in a data center? Was it a whole data center? Was it an entire region? Obviously, we would always prefer a smaller blast radius, a single rack failing to a larger scope failure. So while we do relentlessly focus on preventing failures, and I would say that we've gotten very good at keeping our systems extremely highly available, we also relentlessly focus on reducing blast radius for those very rare cases where we do have a failure, and try to contain it and make it as small as possible. One way we do this is in our correction of errors process. So that's our postmortem process that we use whenever there's an event. The service team will go through, analyze what were the root causes of the failure, and then identify a set of actions to take to prevent recurrence. One of the questions in the template for doing this correction of errors is about customer impact. And we ask, as a thought exercise, how could you cut the blast radius for a similar event in half? So we're always thinking about, even when we do have an event, how can we make it even smaller blast radius the next time? So before talking about how to do that, let's talk about how things can fail. So one way things can fail is while servers crash, maybe not like this, but servers do crash. Disks fail in a variety of interesting ways. They might go completely offline. They might have random I/O errors. Network devices can fail, and if they don't fail, they can introduce random bit flips. We've definitely seen this happen a few times. Meanwhile, outside the data center, utility workers can accidentally cause fiber cuts. You can have electrical storms that can cause utility power failures. In a More extreme scenario, you can have data centers actually get physically damaged by storms or fires. So far I've talked about physical failures, right? But there's also non-physical failures we have to worry about. One is just a surge of traffic, whether it's a DDoS attack or a extreme surge in demand on one of our services, which can cause overload conditions. We have to worry about black swan requests. We actually call these poison pills internally. I've done a little research, and that seems to be just an AWS term. But you can think of these as these particularly problematic requests that are either really expensive or there's something about them that trigger a bug in the system. And these can be particularly pernicious because a client will retry after a failure, and so a single failure can cascade and cause an entire system to get infected. So we worry a lot about these poison pills or black swans. We also have to be mindful of the fact that sometimes a software deployment or configuration change could introduce a problem. And then, of course, most generally, there are bugs. And obviously, none of us want to have bugs get into production, and we have a very good success rate in not letting bugs get into production, but there is still that possible eventuality. And so, now that I've talked about failures and what we mean by blast radius, I'm going to talk about the various techniques we use to contain it. So region isolation, availability zone independence, cell-based architecture, shuffle sharding, and then finally, in tandem with all these techniques, the operational practices that we use to get the desired outcome. So let's start with region isolation. So as you probably know, AWS is deployed globally in 19 separate locations that we call regions. And we actually have 5 additional regions that we've announced that will be coming online soon. And as a customer, you choose the region that you want to run your workloads in based on factors like latency or maybe data residency. Each one of these regions is a separate, distinct stack of AWS services. And each region has a separate set of endpoints for the APIs you use to interact with the services. So for example, in EC2, if you want to interact with EC2 in US West 1, you would use the ec2.uswest1.awsamazon.com endpoint. Meanwhile, if you wanted to use EC2 in US East 2, then you would use a separate endpoint. And the reason is there's no single global EC2. There's a separate stack in every region. And these are isolated instantiations, and they don't know about each other. So this is a shared nothing architecture, which gives us the ultimate in blast radius protection. So there's our EC2, the Amazon Elastic Compute Cloud service in US West 1 and US East 2. They don't talk to each other. They don't know about each other. Same is true for a service like Amazon SQS, Amazon SageMaker, and so on. Now you might be wondering, well, but there are multi-region or global features. You know, what about those features? Things like S3 cross-region replication or Dynamo's global tables, or EC2 virtual private cloud peering. So let me talk about how we address those by going through an example. So this is an example of inter-region virtual private cloud peering. So virtual private cloud, or VPC, basically lets you provision a logically isolated section of the AWS cloud where you can launch resources in a virtual network that you define. You define the IP addresses in your virtual network, configure route tables, gateways, and so forth. And with inter-region VPC peering, you can actually take 2 VPCs in 2 different regions and virtually connect them so that they can communicate without having to go over the public internet. So here's our VPC peering connection. Now, setting one of these things up involves a workflow and a set of approvals, particularly because they can be VPCs owned by different customers. So you want both customers to agree to establishing this connection. And that involves configuration changes in the VPC configuration on each of these, in each of these regions. But these EC2 control planes don't talk to each other. So how do we accomplish this? The answer, we have a dedicated service called the Cross-Region Orchestrator that sits on top of these systems. and implements the workflow, manages through the approval process, and comes through the sort of the front door of EC2 just like any other API would. And it also has a certain number of safety features. It ring fences some of the interactions to ensure that there's no possibility for multiple regions to be impacted by whatever issue there could be at the same time. So we can preserve that single region blast radius. So kind of to recap here, we've got all these regions, and we're deeply committed to this principle of region isolation. So in the event of, say, an earthquake in Japan, which we did experience a few years ago, there could be impact in that region, but it's going to be limited to that region. So in the worst case, we have a single region blast radius in case of a failure. But that's still pretty big, right? That's a lot of impact, especially if you're a customer that sits only in that region. So obviously we want to do better. So how do we do better? Now I'm going to talk about availability zone independence. So let's drill into the design of a region, kind of double click on it, and see how we limit blast radius within a region. So there's our region. A region is actually composed of, well, before I talk about what it's composed of, a region sits in a location, right? So at the macro scale, it's Northern Virginia or Dublin or Frankfurt, but it's not a single data center. It's actually it's composed of multiple data centers that are spread across the metropolitan area of the region. And we call these different locations availability zones, and they're cross-connected with high-speed private fiber links. Now, these are far enough apart from each other that there's a very, very low possibility for correlated failure, except maybe in the earthquake case. So you can think of them as miles apart. And so that means if a tornado comes through, it's unlikely that it would hit multiple facilities. If there's a utility issue, we actually run off of different utility suppliers in a region, so that won't affect multiple availability zones at the same time. And at the same time, they're close enough to each other, so again, think about it as miles away. They don't have that pesky speed of light issues. You can think of them logically being in the same place, run things like synchronous replication protocols and so forth without any latency penalty. So each availability zone is basically n data centers. It's not just one data center. So in some cases, because we keep the size of the data center set to a fixed maximum size, in larger AZs, we might have multiple buildings for an AZ. And then we have n of those availability zones per region, usually 3 or more. In fact, in all future region builds, we'll have at least 3. And that's useful for certain distributed systems consensus protocols that are best suited when you have at least 3 locations, so you can get consensus agreement across them. Globally, we have 19 regions with 57 total availability zones, and 5 more regions coming online with 15 more AZs. So with this architecture of AZs within a region, we now have the possibility to reduce the blast radius because we've reduced the possibility of a correlated failure across the entire region. And you can take advantage of this multi-AZ architecture in your own applications, just like we do in AWS, by using a multi-AZ architecture for your application. So let me go through a quick example here. Super simple. So you have your application that runs on a set of instances that you've deployed across multiple AZs, and then run an elastic load balancer to load balance the traffic across them. And then behind the scenes, you're using a relational database maybe for your persistence, and that's set up in a multi-AZ primary standby pair. So if you have a failure in one of the availability zones, the elastic load balancer will detect that and stop sending traffic to the failed AZ or the instances in the failed AZ. Meanwhile, the application is connected to the master database that has gone away, maybe because there's a power failure or a network failure. But you could fail that database over to the healthy AZ, which happens automatically with Amazon RDS, and then your application is up and running again. And these failure detection events can happen fairly quickly, so there might be a slight hiccup in the operation of your application, but otherwise it's almost like a non-event that you lost one of the data centers in your application. So this is how all of our services that run regionally in AWS are designed and operated. It's a really powerful model because it gives you this fault tolerance, and it basically means that you can withstand an AZ failure and not have any impact on your customers. It's also a powerful design for durability. So S3 uses the multi-AZ model to get its 11 nines of durability. And so with this architecture, you can basically get to 0 blast radius when you have a data center get hit by a tornado or a utility worker cutting a fiber connection. So what about the services at AWS that are zonal? So some of our services give you the opportunity as an application to have zonal resources, like an EC2 instance or an EBS volume. You decide which AZ these live in, and that's part of your story for creating a resilient application. So these are zone-specific resources, and for minimum blast radius considerations, we actually have a zone local control plane for the resources in each of our AZs with a principle of availability zone independence. So let me talk about control planes real quickly if you're not familiar with the term. So control plane is the thing that you interact with to administer these resources, whether they're zonal or regional. And then the data plane is the thing you interact with to actually do the work you want to get accomplished. So some examples are here for Amazon EC2. The control plane is what handles run instances. So it takes your API request and then does all the work necessary to launch the VMs per your instructions in your API. And then the data plane for EC2 is basically the instance, right? The thing you SSH into or that run your application on. It's also the network that attaches your EC2 instance to other instances in your VPC. So let's talk about AZI, or availability zone independence, for these things. So the data plane runs in each of these AZs, and these are isolated from each other. They can obviously communicate over a network, but otherwise the data planes don't really know about each other. And the same is true of the control planes for these resources. Now, I mentioned earlier there's a regional endpoint to access EC2. So there must be some layer that you connect to that sits on top of these. And there's a regional control plane that acts as the entry point and also handles things that are not zone specific. So for EC2, things like security groups are not zone specific. It also aggregates APIs like describe instances. So if you want to find out about all your instances in a region, it will need to interrogate the control planes across all the AZs. So in this model, again, if you lose an AZ, you're going to lose your zonal resources, but you expected that anyway. But the data planes and the other AZs are fine. The control planes for those zones are fine. And the regional control plane is built to be multi-AZ fault tolerant. So it will also continue to operate fine, except for the fact that it won't be able to service requests that target the zone that's down. So if you have API calls to one of the healthy AZs to launch an instance there, it should be able to route around this particular type of AZ failure. Okay, so let's review the blast radius improvements that we get from availability zones. So here's a regional service spread across 3 AZs. If zone A fails, regional service is fine because it's able to fail away from the failed AZ. Meanwhile, a zonal service has an impact just in that zone, but not the other zones. The other zones are isolated, and they won't have any impact. These are all good things. The theoretical blast radius is a different story. So by theoretical blast radius, I mean, in the worst case scenario, the thing that, the black swan event, like what's the worst case that could happen here? For the regional service, it is the entire service. And that's the thing that we lose sleep at night, every night thinking about. For the zonal service, it's still the zone. So there's something nice about this property of these availability zones. We still don't like that there's a non-infrastructure event that could take out a service in a zone, but it is still nice that it's contained to the zone. Can we get the same kind of resilience in our regional service without having to sort of target it in a zone local kind of way? So let's take a step back and look at this abstracted architecture. So there's an entry point, a regional entry point into the service. It has an aggregation layer that might do a few things, but mostly it's a routing layer into a set of compartmentalized resources. And then there's failure isolation between them. So in the availability zone case, these are AZs down here, and then a regional control plane that accesses them. But more generally, there's this compartmentalization that is giving us this nice fault isolation. Can we use that in a different way, in a different dimension than AZs, and get some smaller blast radius? There's another way to think about this abstracted architecture, which is how they build ships. So for centuries now, ships have been built with these watertight compartments that are separated by bulkheads. And the reason of this is that if there's damage to the hull and it causes flooding, the flooding is contained into one of those compartments, and the rest of the ship is still intact and the ship stays afloat. Those bulkheads also provide structural integrity. These are both nice properties, right? You have this fault tolerance, minimized impact of failure, and higher structural integrity. And so we've taken these ideas and applied them to our regional services in what we call cellular architecture, or cell-based architecture. So let me go through our simple example again of an application with a load balancer, compute, and some storage. And it's not shown here, but this is an application that is running in multiple AZs and has the failover as I described before. So in cell-based architecture, we take this service stack configuration and we create multiple instantiations of it. And these are fully isolated, they don't know about each other. And each one of these stacks is what we call a cell. And then we'll take our workload and basically load balance it, partition it over these cells. One way to do that might be by customer. So we'll put this section into cell 0, this section into cell 1, this section into cell n. And now, you guys all look nice, but maybe there's someone naughty in here that's going to cause us a problem. They're only going to cause a problem in that one cell. The other cells are going to be fine. Now we need some way to contain this thing or make this thing look like a single service still. So we put a cell router on top of it that makes those routing decisions. And that whole thing is what we call a cell-based service. So the cells are an internal structure that's invisible to you as a customer, but provide resilience and fault tolerance. And this looks just like the picture for AZI, or availability zone independence, but on a different dimension. So let's talk about what that looks like. So here's the regional service getting resilience from availability zones. Here's that same service divided into cells. And you can see now that with an availability zone failure, both services are resilient to that because they're fault tolerant across AZs. In the other examples of failure, the ones that we lose sleep at night over, the failure in the cell-based service is contained to the cell. So the impact is 1 over n, where n is the number of cells, rather than the whole service. And I've shown 3 here for the purposes of presentation, but the number of cells can actually be much higher. So 1 over n could be a fairly small percentage of the overall set of workloads that you're supporting. Now this approach can also be applied to zonal services, and we do this in our EC2 control plane, where you divide each of the zonal services into cells as well. So you still have a failure as you'd expect if an availability zone goes down. What's interesting though is, as I mentioned, some availability zones are multiple data centers. And so you can actually have a smaller blast radius in certain cases if your zonal cells are aligned with the physical infrastructure, which is the case with our zonal EC2 control plane services. That's actually a nice improvement. And then again, for the other failure cases that we worry about, there is also a smaller blast radius, even for the zonal services. So let's look at the system properties of a cell-based architecture. So we've already talked about some of them. The first one is workload isolation. And this is useful not just for failures, but also just noisy neighbor problems. And then of course, there's the failure containment. So if we lose a cell, the other cells are fine. There's also this nice property that is really powerful, really important to us at AWS, which is how we scale these things. So rather than scaling up a service, which is sort of the traditional way, you just add more and more capacity to it. In a cell-based architecture, you can also add more capacity to cells, But one of the things that we include in our goals for a cell-based architecture is that cells, like our data centers, have a maximum size. We won't let them grow past a certain point. And so if we need to continue to grow a system rather than growing the cells past that point, we'll add another cell. So you grow the system by scaling it out with more and more cells. The fact that the cells have a maximum size means that you can test them at that maximum size with a reasonable test configuration. So you can test them to failure, you can do all sorts of stress testing and get confidence that you understand how that piece of the system is going to operate as you get more and more demand on your system. These cells are also more manageable because they're smaller, so if there's some issue, you need to look through logs or otherwise inspect the nodes in the cell. It's going to be it's just a piece of your system rather than the whole system, so it's going to be easier to work through. So let's now talk about some of the core considerations in a cell-based architecture. So the first is cell size. Sort of the trade-off here is you can have a large number of smaller cells or a smaller number of large cells. In the case where you have smaller cells, that's nice because now your blast radius is that much smaller. And those smaller things are easy to test, easier to break, to understand what their breaking points are. And they're easier to operate in terms of figuring out if there's an issue, smaller number of nodes to go in and take a peek at. On the other end of the spectrum, though, larger cells have some good properties, which is, first, if there's a fixed cost to each of these, which often there is, maybe there's a separate load balancer for each one of them, then you get cost efficiency by having fewer of them. You also get reduced splits. So this is an important consideration. If we're dividing our workload by customer, some of our customers might be large, they have a large number of workloads, and that may be too large to fit in a smaller cell. If we're using larger cells, we may be able to fit that larger customer into a single cell and not have to worry about the complexity of splitting across multiple cells. And then finally, as a whole, this system that has fewer cells is easier to operate because it's easier to think about, easier to look at dashboards and so forth. There's no right answer here, except that all things being equal, we will always prefer the lower blast radius to these other considerations. Another, which I'm sure you've been thinking about looking at this diagram, is, well, what about the router? The cell router is this remaining shared component across the entire system. And so it's really important that that thing not fail, because now you're back to the regional blast radius. And so we spend a lot of effort making sure that that component is stress tested and battle hardened so that we know that we have high confidence that even in the black swan scenarios that it's going to stay resilient and stay up. And one of the ways to accomplish that is to keep it as simple as possible. So when we talk to teams about adopting cell-based architecture, we call this component the thinnest possible layer to kind of reinforce. It should be really simple. And yeah, that's all I'll say about that. Another consideration is partitioning dimension. So I've talked about how we might divide cells along lines of customers. But then in the EC2 control plane case, there's an aspect of the control plane that actually is cell-based, based on physical infrastructure in our data centers, which makes sense for that application. In another scenario, we may divide not by customer, but by VPC, especially because sometimes VPCs may have cross-customer scenarios. And so it takes some analysis to decide what's the right way to carve this thing up. And the recommendation I always use is cut with the grain. And if you don't know what that means, then think about it this way, that wood has a certain grain, and it's easy to split along one dimension and really hard to split across the grain. And every system has a natural grain to it. Another consideration is what I call cross-cel use cases. So these may be unavoidable. The goal is to keep them to a minimum because that adds complexity to the thinnest possible layer and also increases the blast radius for those operations. One example is scatter-gather queries. So what this means is there may be an API that comes in that needs to interrogate multiple cells. So scatter requests out and then gather responses to send out a single reply. So an example in EC2 is the describe instances case I mentioned earlier. Another is batch operations. So if you need to execute work on multiple cells in a single operation. So again, EC2, maybe the terminate instances API, where you can send multiple instance IDs. That could be a cross-cel use case. The last and probably the hardest is coordinated writes, where you're actually trying to do something atomically, but across multiple cells. So those require careful consideration, and one example of that is cell migration. So cell migration is when you relocate a workload from one cell to another. So maybe we decide this customer, we're going to move that customer into cell 2 from cell 1. And you may choose to do this because you want to manage the amount of load or heat that's on each cell, or maybe you just want to load balance the sizes of them, or maybe you've added a cell and you need to, and your approach for adding cells involves moving existing workloads over into the new cell. And the process that you use to do the migration is not unlike a VM migration. So if you're familiar with how VM migration works, basically there's a invisible clone that gets created in the target location, and it gets brought up to date and synchronized with the source. And of course, the source is still changing, so this can take a while for it to get close to being in sync. And then at the last possible moment, both are frozen for the final completion of the syncing, and then an atomic flip over to the target location. So that works for VMs, and that's the same approach that we use for migrating workloads across cells. So it requires some careful coordination, best managed at the router level. And we have a few approaches that we've been using to accomplish this. So again, with the cell-based architecture, we're able to reduce the blast radius from 100% down to 1/n, where n's the number of cells. I should reinforce that the events that cause these types of outages are exceedingly rare. We could spend a long time not even having to worry about this kind of failure happening because of all the other things that AWS does. But we're so focused on resilience that we're investing additional engineering work to get to that picture on the right, which is a smaller blast radius even when those black swan events occur. So cells are great, but there's another technique that we've been using that is even more impressive and more exciting, I think, which is called shuffle sharding. And shuffle sharding is a technique that is like cell-based architectures, and is particularly useful in stateless or soft state services. So let me walk through what shuffle sharding looks like. So here's another simple service. We've got 8 nodes, and these 8 nodes are handling requests that are sent by a load balancer. And then we have 8 different customers that are sending requests. So we're in Vegas, so I use some gambling relevant icons here to represent our different customers. And let's imagine one of them, Diamond here, is introducing a bad workload for whatever reason. Maybe it's an expensive request. Maybe it's one of these requests that triggers a bug in the system. So Diamond sends a request in, and that request causes one of our servers to crash. Okay, it's all right, we've got 7 others. Maybe Diamond will go away or change what it's doing. Probably not, it'll probably keep retrying and eventually take out the whole system. So here our blast radius is basically all the customers. Right? This is like the worst case scenario. We really want to avoid this. So this is where we go to cell-based architecture. So we divide up our customers, assign a subset of customers to each cell. Now when Diamond comes along and causes problems, that problem is contained just to the cell. This is a 4x improvement, right? We've gone from 100% down to 25%. The blast radius is the number of customers divided by the number of cells. And again, we could improve that further by adding more cells. Or in a system where we don't need to really worry about which customers land on which nodes, we can shuffle shard them, which is a little bit different And it's nuanced, but you'll see shortly how powerful this is. So we'll take each customer and assign them to 2 nodes, effectively at random. Not really random, we'll use hash functions to be predictable about where these customers land on these nodes. But basically, we've assigned them at random. So Diamond gets assigned to the 1st and 4th nodes. We'll put spades on those 2. Our roll of 2 on the dice goes to those 2 nodes, and so on. So these are basically shuffled randomly across our set of capacity. So now again, Diamond comes along, takes out the 2 nodes that are assigned to it. But here's where it gets interesting. Look at who's sharing those nodes with Diamond. One of them is Hearts. Hearts, however, has a 2nd node that it's assigned to that's not impacted by the outage. So as long as that customer retries, it's fault tolerant. Even though one of its nodes is down, one of its nodes is up, it's able to continue operation. The same is true on the other node, where Clubs has that same property. So in this case, our blast radius is actually the number of customers divided by the number of combinations of 2 pairs out of 8, which turns out there are 28 of them, which is 3.6%. So if we had a much larger number of customers, we'd expect, if these are well distributed randomly, you would have 3.6% of customers impacted by the failure that I showed. Meanwhile, less than half of the customers would be in that scenario where they're sharing at least one of the nodes. So they may see a little bit of impact, a little bit of hiccup, but they're fine. So we went from 25% down to 3.6%, going from the cell-based down to shuffle sharding. Now this is a small system. Oh, I should show you the math. So the math here is probably, as you remember from high school, the binomial coefficient. As you look at this math, you'll realize as n grows, our number of combinations grows really quickly. So let's say we go from 8 nodes up to 100. 100 is not a large, like a huge number of nodes. It's a reasonable number to run in a large-scale system. So let's say we have 100 nodes, and then we give each customer 5 combinations, or sorry, 5 nodes to represent their combination. The math tells us that's going to be 75 million different combinations. Think of it basically as a deck of 100 cards. There's 75 million different combinations of cards you can get by picking randomly from that deck, which is amazing because now you can see, all right, 77% of customers are not going to see any impact when Diamond comes along and takes out its 5 nodes. But more interestingly, 99.8%, so those first 3 rows, are still going to have a majority of their nodes available. So they're going to have a better chance than not to completely route around that problem without even having to try. And meanwhile, that very, very low percentage of customers is basically the percentage of customers that are going to be sharing completely those same 5 nodes. What's magical about this, and it's all in the math, is we've created a multi-tenant system and then use the shuffle sharding to create basically a single tenant experience, which is obviously what AWS aspires to do. Now this needs a fault-tolerant client, as I mentioned. So one that, when it gets a failure, will retry, but that's not hard, that's pretty common. What's interesting also is this not only works for servers, it can work for queues, it can work for other resources. It's also critically dependent on fixed assignments. So you're stuck with the hand that we deal you. If there's any sort of failover, like, oh, well, your 5 nodes are down, I'll give you these 5. Then you get back into that old world where now a problem can infect and cascade across an entire system. So it really depends on those fixed assignments. And then finally, you need some sort of routing mechanism. So either a shuffle sharding aware router, or DNS can be another. So in some of our services, we'll hand a customer-specific DNS name, and that will resolve to the customer-specific shuffle sharded set for that customer, which basically gives them the routing for free. Cool. So let's talk about the operational practices that we now layer on top of these architectural techniques to achieve the lowest possible blast radius. The first is not even a practice, but really a mindset and maybe even a religion at AWS, which is probably best captured by Werner's blog from earlier this year about compartmentalization. And that's this, actually I'll just read it. So I won't do his accent. I don't know if you've seen Werner talk, but I'd wager that every new AWS engineer knows within their first week, if not their first day, that we never want to touch more than one zone at a time. This is so important because if we have availability zone fault isolation, or we have region isolation as a core tenet of our blast radius reduction, that's going to go out the window if we have some correlated failure introduced by some manual action or automated action on multiple of these at the same time. The most common and most, I guess, obvious example of this is with software deployments. So our software deployments are done in a staggered way across zones, across regions, over time, quickly enough that we can get features out to customers that, because we like to launch features, but slowly enough that we have confidence that as we're pushing this change broader and wider, that it's not going to cause an issue. So we'll start slow, observe, test, and then maybe speed it up as it goes out broader and broader. And that's the case with cells, it's the case with availability zones, the case with regions. And then within each of those deployment units, we'll do a fractional deployment there too. So a one-box test as the very first step for a service. For our EC2 harbor deployments, we'll start with maybe 5 or 10 machines at first, verify that things are working, and then gradually speed it up as it expands across the infrastructure. In tandem with that, we have a bunch of automated tests that run as part of the deployment, as well as canaries, or these test applications that are mimicking a real-world customer invoking APIs. And we'll monitor the results of those. And if there's any problem, the deployment will get automatically rolled back. We'll look at what happened and either decide it was not an issue that we need to worry about or fix the problem before we start the deployment again. So this is really important. This is what we need to do to make sure that we've not compromised the boundaries that we've put between cells and AZs and regions. All that deployment machinery is automated, including the rules about the tests that have to succeed, including the timing and the windows of when we progress to the next stage. But automation's a key in general, right? It's not just deployments. There are other things that we do with our infrastructure to manage it, whether it's configuring network devices or propagating new credentials to the stacks. That could be done by hand, but humans are prone to error. It's much better to automate it, particularly because you can review whatever it is that you're building in your automation. You can test it. It's predictable in how it's going to operate, and you can repeat it over and over again and know that it's going to work the same way every time. And then finally, as you may have heard, AWS and Amazon in general has a very strong philosophy around end-to-end ownership. So our service teams are composed of engineers who are builder operators. So as engineers, we build the software, we design the software, we test it. We also are the ones that deploy it, and we're the ones that operate it and respond to issues in production. What this does is it gives us this wonderful opportunity to have a feedback loop in terms of design choices, what the impact is operationally, and then understanding what changes we need to make to avoid future problems when there is a failure that we need to worry about. And so I mentioned earlier the correction of errors template that we use. That's usually filled out by engineers or in partnership with engineers, where they think about the blast radius. And so they're in a great position to then go and implement the changes to make sure the next time, if that event occurs, the blast radius is cut in half or more. So to wrap up, we've got a variety of containment, compartmentalization mechanisms that we use to reduce blast radius. It starts with regions and the strong isolation between regions. Then it goes into availability zones, and then this alternate dimension of availability zones, compartmentalization, which are cells. And then the magic of shuffle sharding to get sort of virtual cells, and and taking advantage of the combinatorics of the shuffle sharding. And then with those, we protect that compartmentalization with operational practices. So step-by-step phase deployments that are automated, and then service teams that are builder operators, so they are close to the front lines and understand how their decisions are impacting the availability of their systems. And all with a goal of reducing blast radius. So that's my talk. I hope you learned a few things, and I'm happy to take questions now if anyone has them. And I think there are live microphones down the center aisles here. Yeah, so the question was, is there an example of Murphy's Law where we thought we had everything nailed down, everything sorted out, that we'd answered all the possible failure modes? It goes back to my slide of the bit flips on the networking side. So this is an example from many, many years ago. So in S3, S3 cares deeply about data, cares deeply about the integrity of data. And there are many layers in S3 of checksumming. So if there is an errant bit flip introduced, we make sure it doesn't, we detect it, it's not an issue. In 2008, we had an event in S3 where there was one network card on one server that every now and then was flipping one bit. And there was a layer of the system that handles basically the group communication across the system, uses gossip protocols, so it can detect whether, I can understand what the state is of all the servers in the system, whether they're healthy or not. Well, the gossip protocol noticed there's a funny server name in this packet because one of the bits was flipped in the server name. I never heard of that host before. And it triggered a much more expensive sort of reconciliation protocol. Long story short, and you can read the long story, there's a postmortem that's still published on the somewhere in the dashboard, status dashboard pages. It talks about the outage, but it took down S3 completely. So one server, one NIC, one bit took down a regional service, and that was the only layer. We had checksumming all the way up and down the stack. That was the only layer that didn't have the checksumming. Somehow we'd forgotten to add it there. Yeah, so the follow-up question here is, wasn't there a more recent event where there was a human error involved in an S3 event? And yes, there was. And this comes back to my operation practices slides I was talking about, which is all your best plans can fall apart if whatever you're doing doesn't respect those fault isolation boundaries. In this case, the engineer very certainly knew our philosophy, and it was more of just a human error mistake on the command line, which comes back to the importance of automation and the importance of testing of those things.
Peter.
Yes.
With everything that you talked about in the different layers, from regions, availability zones, to cells, to the shuffle sharding, to your customers, are they given to them, or are they for purchase as services?
Good question. So regions are given to you. AZs are given to you. Cells and shuffle sharding are sort of different things in that they're like the watertight compartments inside the ship. So you could ask the purser on the boat to give you a tour of the lower decks, and maybe they'd show you the compartments, but otherwise you don't really care about them, and you get them for free. It's just part of the safety of the ship.
Thanks.
So they're invisible and they're free. Over here.
I think my question is sort of the same, but I'm actually not sure. So
Okay.
if as a customer I wanted to have a cell for my own service that I'm making, and I actually care about aligning that cell with a particular data center, is that something I can do as a customer? Can I say, I want these all to have affinity to the same data center, all these EC2 instances?
So you can get that kind of affinity with your zonal resources, right? So you can get affinity with your EC2 instances and your cloud HSM instance and your EBS volumes, because we give you full control over
To the data center?
the place. Well, an availability zone you can think of as a logical data center. They're one and the same.
Okay.
So a data center will always be in one AZ,
Right,
and an AZ will always be one or more data centers.
right, but my
You're
understand-
saying for the multiple data center AZs?
Exactly,
Got it.
yeah.
No, that is not visible to you as a customer. You don't have control over that.
Thanks.
Yep.
So as you move from regions to cells, how does the version management of stuff that you're deploying, is there any operational insight into that of the software being deployed there?
I mean, how do we keep?
Does it have any impact on, managing operations deploying in a region versus deploying at a shard level?
I see.
Are there any complexities there?
Yeah. So I think what you're saying is there's this window of time when we're going through the progression of a deployment, and the versions may not be in sync across multiple locations. Is that the core of your question?
Yes.
Yeah, that's definitely a consideration. And a deployment may take, depending on the system, it may take several days to several weeks. In some of our infrastructure, we're particularly careful about the pace of deployment. In fact, in some of the networking components for VPC, it's a particularly delicate affair to roll out changes, so it might take a while. So yeah, that is a complication that we have to be mindful of, well, which version is running here?
Yeah.
Yep.
Yeah, hi. Some questions regarding the global services. You talked a lot about regions, availability zones. How are the global services regarding control plane, data plane, resiliency in respect to the regions or edge nodes and organized?
So is your question about
For example,
regional services that have global features or truly global services?
For example, IAM.
IAM, okay. Yeah, that's a great
one
question.
example.
So IAM is a special case because your account information and your credentials and so forth are available globally. So it is, in a sense, a global service. However, each region has a separate control plane, a separate data plane that can operate completely disconnected from the source of truth for IAM. The control plane, however, is global, and so there are particular considerations that we take with a service like that to make sure that it continues to be available even in the face of some of the failures that I talked about. But actually, I had it on the slide and I forgot to mention that there is another philosophy that we have, which is this separation between control plane and data plane, and ensuring that the data plane can continue to function even if there is a control plane issue, and that's exactly the scenario in IAM. That's critically important because a region can be disconnected from the source of truth, or there could be other issues with the control plane. We want to make sure that you can still, validate your credentials and so forth, in each region and not have global impact. Can you go to the mic?
So when you were talking about the cell structure and
Yeah.
then the shuffle sharding, when you were talking about the cell stuff, you were talking about in the control layer setting out the routing to cut with the grain of the service. There's logical ways to break it up. When you move to shuffle sharding, is that done at the same level? Because obviously you lose that sort of control based on the characteristics of the service.
Yeah, it's a good question. And for cell-based services, usually the thing that prevents you from shuffle sharding is that you have to have some control over state. So you can't just sort of willy-nilly scatter state across the entire fleet. Some servers don't have state, or there's soft state that they can cache locally and then operate fine. The shuffle sharding works well for the latter scenario, where there doesn't need to be any particular node affinity. There's another sort of advanced topic here, which is kind of interesting, which is you can actually layer both of these things together. Because you could take a cell-based architecture and then shuffle shard requests across them in a stateless system to get a different kind of resilience property. And that's something that we're working on now with DynamoDB. So I don't know if I answered your question. Okay. So I guess maybe another way to answer to that is shuffle sharding is not an improvement on cell-based in all cases. It's really system specific on when you might be able to apply it. Cool. Okay. Looks like there's no more questions. Thanks again for coming. Hope you learned something and enjoy your week at reInvent.